They're online. I sent a note at 1. Sorry. Yeah, the slides are online. Some of you have asked me, why aren't the slides online like 2 days before the lecture? The sad truth is it's because I prepare the slides right before the lecture. But when I do put them up before a lecture, I send out a note. So I did, for example, today at 1. But, you know, this way this stuff is fresh in my head, and so it's easier for me to get into the material. And, well, and I apologize for the fact that they're not ready sooner than that. So let's see, a couple quick announcements before we start the class today. As you've noticed, homework 1 is due. Some of you noticed that some of the problems were more challenging than others on homework 1. The question about Poisson distribution was a little bit more challenging. That was there partly to remind us all that there are a lot of different kinds of probability distributions that you probably saw in your statistics course. And the fact that we don't talk about every single one of them in lecture doesn't mean that you shouldn't know about these or be able to just pick up a new one and understand what it means. So that was kind of an opportunity to look at it that way. The next homework assignment will be out in the next day or so. We'll send it out electronically. And it includes a question where you get to implement naive Bayes and apply it to document classification, which is something we'll talk about today. Part of my goal in this class is by the end of the class, I'd like you to have a kind of mix of theoretical understanding of the principles and the algorithms in the field, but also have an exposure to at least a small number of algorithms that you've implemented or experimented with yourself. So this next assignment will be a chance to implement naive Bayes, which you now know is a very simple algorithm, and test it out on some text data. I'm hoping that later on in the semester we'll have another programming assignment that will give you a chance to apply machine learning algorithms to some image data as well. So I find for a lot of people who I talk to feel like, well, text and image data are especially weird kinds of data. They're not structured data the way a database, structured database would be. And so it's interesting to see how we can apply learning algorithms to those. The final thing I wanted to say is that there will be, as you've noticed on the course webpage, there will be a project a more substantial project that you'll get to do mostly after the midterm. And the number of homework assignments will decrease dramatically at that point because we'll be expecting that you'll be working on your class project. And we're going to put up a collection of many, like well over a dozen, different data sets that you can define a course project around. And we'll have some suggestions of problems you might look at. You'll be, if you feel like teaming up with another student, we'll be happy to accept teams of up to 2 students to work together on a project. And also we'll be very happy to have you propose your own data set. For example, some of you I know have already talked with me about projects that you're involved in for other reasons. And if you want to design your course project around your own data set, you're welcome to propose that to us. We'll ask for proposals just after the midterm. But the one reason I wanted to bring this up now is so that you could start thinking about it, and also because I wanted to let you know that there's only one rule about bringing in your own data, which is you must have your own data before you submit your proposal. And so if you're thinking, oh, wow, I'd love to collect some data and do a proposal around it, then you should begin now to collect that data. Because we will approve only proposals that say, I already have the data, here's the file pointer to it, and here's what I want to do with it. And that's simply because over time, we've learned that it can take longer than expected to collect data, and you don't want that clock ticking while you're trying to do your project. Okay. So any questions about the projects or other of those kind of logistics issues for the class? Oh, one other quick thing. Many of you have noticed this because it's on our website. But my office hours are right here in this room immediately following lecture every day. So feel free, if you want to follow up on any of the issues in class, to just hang around a little bit after class. Okay, so that's it for announcements. Today's lecture. So we're now at the point in the course where we're taking very seriously the idea that we want to design machine learning algorithms that have a principled probabilistic foundation. So unlike decision trees, which were kind of a reasonable heuristic scheme for growing something that fits the data, we're now really looking at the question of how can we design function approximators or systems that predict the conditional probability of our target label y from the attributes x that are available, that are based on Bayes' rule, and what does it mean to learn the parameters that we need in order to correctly capture p of y given x. And last time we talked about naive Bayes. I want to not restart. Let's postpone. Okay. So just to remind us all, the beauty of naive Bayes is even if you forget it, you can rederive it. It's so simple. Okay. So here's naive Bayes in one slide. Of course, we all know Bayes' rule. You shouldn't try to rederive that. You should, you should know you should know the Bayes' rule, which can be written in a couple forms, but here's one of them. And then the naive Bayes rule is simply the consequence of starting with Bayes' rule and making a conditional independence assumption. And the conditional independence assumption simply says that we can write the joint probability of x1 through xn, given some y, as simply the product of the individual probabilities of the x sub i's given y. Right? And that's why when we trained the now famous Squirrel Hill classifier in class last time, where our xi's were G, do you shop at Giant Eagle? D, do you drive to work? And M, are you a Rachel Maddow fan? So we had a Boolean variable, do you live in Squirrel Hill, that we were trying to predict from x1, x2, and x3, these other three Boolean variables. And instead of estimating all the different, 8, 2 to the third possible configurations of those x's, we just got, for each variable individually, like do you shop at Giant Eagle, we just used U training examples to estimate the probability that you would shop at Giant Eagle, given that you do live in Squirrel Hill, and also the probability that you'll shop at Giant Eagle, given that you don't. Right? And we did that because we were making this conditional independence assumption that essentially says, well, we're going to, under this assumption, compute this joint probability as simply the product of the individuals. And that way, instead of having to compute 2 to the n, order of 2 to the n different parameters for our n x sub i's, we could just get a number of parameters linear in n. Okay. So that's, of course, the idea of naive Bayes, and that's all there is to it. And then, of course, if we're given some new x, like one of our test examples, to predict y for, then we simply look at that new test example. We see what its xi values are. Does it shop at Giant Eagle, and so forth. And then we calculate the probability of y taking on its different possible, any particular value, just using Bayes' rule and using those estimates that we have for the probabilities for the values of x that we observe in our test example. Okay? So very straightforward. And so that's exactly how we can get the probability of y given x. In fact, if we only care about what's the most probable value of y, for example, if y is Boolean, we just want to know yes or no, do you live in Squirrel Hill, what's more probable, then all we have to really look at is the numerator in that second expression. And we could just assign y to be the value that maximizes the numerator. And of course, the reason we can ignore the denominator is it doesn't really depend on yk. That denominator doesn't depend on yk. Okay, so that's naive Bayes in a nutshell. And I want to start out by actually looking at naive Bayes in a slightly different way. So we could state the decision rule. Do we assign Squirrel Hill equals 1 or Squirrel Hill equals 0? We could use that decision rule on the previous slide. But an equally good equivalent decision rule is to just look at the ratio of the probability of that y is 1 versus y is 0, given the observed features x1 through xn. And we can simply say, well, we're going to look at whether that value is greater or less than 1. Well, greater or less than 1. Get away from me. Okay, and obviously if it's greater than 1, then we're going to assign y equals 1. Otherwise, we're going to assign y equals 0. Okay, now the reason I wrote it that way is it lets me easily point out that that decision rule is equivalent to looking at the logs of those. Right? So I could also look at the log of this ratio and just ask whether the log is greater than or equal to 0. It's the same as asking whether the quantity is greater than or equal to 1, since the log of 1 is 0. So I can look at the probability that y equals 1, given all my features, compared to the probability that it's 0, given all my features. And if I expand it out this way, oh, we didn't say, but I assume you all see why this expression on the right follows from the expression on the left, right? This thing on the right is just, if we take the numerator over here and apply Bayes' rule to it, then this is the numerator that we get in Bayes' rule. And if we apply Bayes' rule to this, this is the numerator we get in Bayes' rule when we apply to that. And they have the same denominator, so they cancel out. Okay. So now let's carry through our log on this version. I'm going to write it this way. I'm going to write it, let me pull out this first piece. Let's take the log of that. And of course, the log of a product of terms is just the sum of their logs, right? So I can take the log of that plus the log of this remaining quantity. And, oh, well, we just said the log of a product is the sum of the logs. So the log of this thing is really the sum over I of the log of P of xi given y equals 1 over P of xi given y equals 0. Oops. equals 0. Okay? It's just the log of the product is the sum of the logs. Okay. Now, this is kind of interesting because what it says is the decision criterion that I've got here is to ask whether some quantity is above or below 0. And that quantity is the sum of these two terms. And you can see the first term just has to do with the priors. What's more likely, that y equals 1 or y equals 0 a priori before we see any x's, plus a term that obviously depends on the x's. And in fact, for each x depends on the ratio of the probability that x will have its observed value given that y equals 1 compared to if it would have that value given that y equals 0. Okay. So now let me go back. Before we were using this notation that the parameters we were estimating, we were using theta to indicate these parameters. So let me say we want to train this naive Bayes classifier. Then, of course, we're going to learn a collection of parameters like the ones we did in the Squirrel Hill example. Let's say theta ik is just the probability that feature xi has the value 1 given that y has the value k. So that's obviously one of the parameters we're going to estimate. I'll put a little hat on these things to indicate that they're estimates. Right? And quick review. If I want to know this value, what is it? It's just 1 minus that first thing, right? They got a sum to 1. I guess I'll put my hats here for consistency. Okay, so those are the things that the parameters that we estimated, for example, for the Squirrel Hill example, and that we'd estimate for any naive Bayes classifier in addition to, I guess, these priors we estimated too. Okay. But so now let me write this out in terms of those. So the question I'm asking is 0 greater than or less than this quantity up here. So let me just, I'll leave this in this form because you all know about, these are just constants, these two probabilities, right? Plus, and now let me write this sum here in terms of the thetas that I learned from my training data. So what's that going to look like? Here's a kind of common and convenient way to do it. Let's say I'm going to sum over all the features. I'll just write it down this way, and then we'll go back through and see why it's the case. X is, here I'm assuming Boolean y and also Boolean xi's. Okay. So xi is either going to be 1 or 0. You're either going to shop at Giant Eagle or not. So I can write this ratio as xi, that'll be 1 or 0. So here's a term when xi equals 1, then what I'm going to want is the probability that xi equals 1 given that y equals 1. Well, that's just theta xi equals 1 given that y equals 1 over the probability that xi equals 1 given that y equals 0. Right? And that'll handle the case when xi equals 1 because we'll multiply that term by 1. And then I can add in a 1 minus xi. And this term, of course, will end up being 0 when xi is 1. But it'll be 1 when xi is 0. So this little linear sum is just a way of building a little selection, an if-then statement, into my equation, right? And now, if xi equals 0, then this term will be 1. And so now I want to multiply it by the log of what? Theta what? Yeah. I actually want this other thing, right? I want the probability that xi will be 0 given that y equals k. That's 1 minus theta. So 1 minus theta I1 will be the probability that y equals 0. 1 minus theta I1 will be the probability that xi takes on the value 0 given that y equals 1. And then I'll divide that by 1 minus theta I0, which is the probability that, oops, my hand made the 0 into a theta. Okay. So you see what I've done? It's just a simple little common trick of using a linear expression as an if-then statement. So if x equals 1, the first term will be used, the log of theta I1 over theta I0. And if x equals 0, that first term will be canceled out, and I'll use the second term instead. Now, why did I go to all the trouble of doing this? It's because this is very cool. Look what we've just done. We've shown that the decision about whether we are going to assign y equals 1 or y equals 0 is a linear function of the x's. It's a simple linear function. You could rearrange the terms there and just show that, you know, if you have x1 through xn, then there are n plus 1 terms in that expression. There's a constant plus some coefficient in front of all those x sub i's. So that's pretty interesting. What that says is a naive Bayes classifier defined over at least these Boolean y's and Boolean x sub i's always ends up being a hypothesis that forms a linear decision surface for separating out the instances x, the x vectors that we're going to label y equals 1 from the ones that we're going to label y equals 0. Pretty interesting. So, and just like when we thought about decision trees, thinking about the form of the decision surface is a helpful thing to consider. For each of the classifiers that we go through, each of the function approximation methods that we go through in the course, you should kind of get your head around what's the form of the function that we're learning. And in this case, it is exactly a linear decision surface. Again, in the case where y and x are Boolean. Okay, we'll have more to say about this, but it's just a property of naive Bayes for Boolean variables. Very interesting. All right. We don't need to go there. Let's move on to now how I want you to help me design a classifier, a spam classifier. Okay, question first.
So what about non-Boolean?
Right. So the question is, what if x and y are not Boolean? Well, we haven't said anything about that yet, but we will. And the interested observer could speed ahead and think about that question. It's a good question to think about. What if they're not Boolean? And we will have more to say about that. But so for now, let's look at text classification. For example, you might want to train a naive Bayes classifier to detect spam. Here's an email I received this morning while I was preparing the class lecture. And you can see in tiny font it says, "I am pleased to announce that Bob Friedriching of the Language Technologies Institute is our new Associate Dean of Graduate Programs, etc." So there's a prototypical example of a text document, and I might be interested in training a classifier to detect which of these arbitrary emails coming in are spam. Or other functions like which emails promise an attachment. My Google Mail reader, if I try to send an email that promises an attachment but I forget to attach it, it often pops up a little warning saying, do don't you want to attach something here? Which I think is very cool. It's based on a machine learning algorithm. So, so the heart of the question is, how can we convert this text document into something that naive Bayes can digest? Well, we know what naive Bayes can digest. It's a vector of x1 through xn variables. So far, we've only talked about discrete valued variables. In fact, we've only talked about Boolean valued variables. But it's pretty obvious that naive Bayes could be extended to discrete valued variables that aren't just Boolean. So how can we do this? Well, obviously, you can make up any kinds of features that you like. And for example, we could have a feature like, does this email contain the string of words won $1 million? There's a feature, and that could be a Boolean feature. And we can make up other features and put them in there. But I want to consider two particular and fairly obvious formulations of the naive Bayes, of text classification as a naive Bayes problem. So basically what we're going to say is, suppose we're going to do y is Boolean, like spam or not spam. And x is going to be a vector of random variables, right? And we're going to learn p of y given x using naive Bayes. And so how can we define random variables exactly? So one answer that's kind of obvious is we could define a random variable for every word in English. Or maybe we just, does anybody know how many words there are in English? I think nobody really knows. But my friends in the Language Technologies Institute tell me that, they haven't really tested me, but they tell me that my vocabulary is around 50,000 words. And yours too. So roughly 50,000 words in an adult English speaker vocabulary. Should we restart the computer?
No, because it took 4 hours.
Postpone. I like the tension, don't you? All right. So let's make a collection of Boolean variables, one for every word in the English vocabulary. There will be, let's say, we'll only use the 50,000 most frequent words in English. We easily have enough text to estimate the 50,000 most frequent words. And then the value of that of each of those 50,000 variables will be 0 or 1, depending on whether that word appears in the email document. Okay, so the value of x sub pleased would be 1 for this document because I see the word pleased up there in the email. The value of x sub aardvark would be 0, etc. So there will be 50,000 of these. Okay, and is this a feasible thing to do? Do you see any problem? Suppose I gave you, let's say, well, I have tens of thousands of emails, but let's say I gave you 1,000 emails that were spam and 1,000 that were not spam, and they were emails that looked like, that kind of thing. Is this a tractable thing to do? Could we actually train a naive Bayes classifier with 50,000 variables?
If there are 50,000 variables, you need linearly many documents. You need the linear number of documents, which thousands, like 2,000 isn't enough.
So there was a comment here which I think I don't agree with. The comment was, well, if we have 50,000 variables, we need 50,000 training documents. I think I don't agree with that. I can see where you're coming from when you think that. But if we think about how we're going to estimate these, we're going to take maximum likelihood estimates, right? Well, let's say we could do map estimates, but let's start simple. We're going to do a maximum likelihood estimate for the probability that x sub pleased will be 1 given that this is spam and given that it's not. I just told you we could have 1,000 spam documents and 1,000 non-spam. So for X sub pleased, I can just count how many of those 1,000 spam documents contain the word pleased and how many don't. That'll give me that probability. And similarly for the non-spam documents. So the kind of nice thing about this is we get to, in a sense, reuse all 2,000 of those documents again for every one of these parameters that we're estimating. So it's not really the case that we need a separate document for each of the parameters, because we get to reuse those documents. Yes?
I don't know how much this would affect the performance, but I do not believe that all the words would be conditionally independent.
Good point. So the comment here is that these words aren't really conditionally independent. That's true. And we're going to hide, well, we're not going to hide. We're going to embrace that fact because we understand these words are not conditionally independent. But as Al Franken used to say, gosh darn it, naive Bayes is a good method and we're going to use it anyway. But I agree, that is a problem. So issues, you see the little issues thing here. The conditional independence assumption false. Okay, that's an issue. But given that we're talking about naive Bayes, that's going to be an issue with any framing of it we have. Yes?
You don't have context for the words?
Yeah, right. So we don't have context for the words, which I guess is another shade of this statement, right? The context is like saying they're not conditionally independent. Here's another one that actually I think bugs me the most. My emails contain different numbers of words. Some of them are short, some of them are long. And so if I try to estimate from a collection of these different emails the probability that the word pleased will occur in a randomly drawn email, of course, an email that's 10 times longer is more likely to have pleased in it than an email that's shorter. And I'm estimating this Boolean variable on the document from documents that are of different lengths. So it's kind of missing some information there. And it's also missing, of course, information about how many times the word pleased appears in the document. Okay, so those are a couple issues. So let's move on to a second formulation, which I like better, which is this. Instead, answer 2, let's say the xi, our xi's are going to be random variables that represent the ith word position in the document. So what does that mean? Well, here's a word position. That's the first one. That'll be x sub 1. Here's another. That'll be x sub 2. Here's another that's x sub 3, and so forth, okay? Here's x sub n. And what's the value of these? Well, it's going to be the word that's there in that position. Okay, so the value of x sub 1 is I. It says I am pleased. X sub 1 equals I, x sub 2 equals am, and so forth. And to make this feasible, I'm also going to introduce a new assumption that we didn't talk about before. I'm going to assume that these different x sub i's, so what are, for a moment, let's just think about what these x sub i's are. So they're random variables that can take on any of 50,000 values. So each of these random variables is like a dice, or a die, a singular die, with 50,000 sides. And every time I want to do a random draw of x sub 1, I'll just roll the die for x sub 1, and it'll generate, according to probabilities of those different 50,000 sides of the dice, it'll generate me a random value for x sub 1 according to that, the probability distribution associated with that die. And then I could have a different die for x sub 2 and so forth. But that would give me a lot of parameters to estimate. I'd have 50,000 minus 1 parameters for each position in the document to estimate. That'd be a lot. So I'm going to make this additional assumption that those different x sub i's are IID. They're independent, of course, at least conditionally independent, because we're talking about naive Bayes. But also I'm going to assume they're identically distributed. That is, the probability distribution over words in position I in the document is the same as over position J. In other words, I'm going to roll the same die every time I want to, for every one of these word positions that I want to sample. So I'm going to have a probability model that says these different xi's can take on 50,000 values. There are 50,000 probabilities associated with those 50,000 words. But it's going to be the same die for every position in the document. And you see why I want to make that assumption. That's going to now shrink the number of parameters that I need to estimate to how many? Precisely? If I have 50,000 words, 50,000 sides of the die, I need to, well, they have to sum to 1. The die has to come out something. So I have to estimate 49,999 parameters in the 50,000th one I get for free. But I have to have a die for when y equals 0 and a different die for when y equals 1. So I need 2 times. So I need 100,000 minus 2. And then what else? So I need the priors on the 2 classes. Oh, that's just one parameter, right? The prior is the probability of a random email being spam. That's one parameter, and 1 minus that is it. So I need 99,999 parameters estimated if I'm going to train this model. Okay. And that's not crazy, it turns out. That's not so crazy. If I give you 1,000 documents, let's say each of them on average has 100 words in it, and I give you 1,000 spams and 1,000 non-spams, I'm giving you 100,000 words worth of text for each of those classes. And I'm asking you to estimate roughly that many parameters. So maybe you'd be happier if I give you 10,000 documents that were spammed and that weren't. But you see, we're in the ballpark. It's not ludicrous. Okay. Is there really a way I can get rid of this? Okay, that takes away half the fun, but I'm with you on this. Okay, so, all right. So this says basically what we just said. So I can think of this probability model as assigning a probability to a document. Document has a collection of words. It's going to be it's as though I'm generating, if I want to generate documents at random according to the probability distribution, the model that we've got, it's as though what I'll do if I want to generate a random spam, I'll take the spam die and I'll roll it, and whatever word comes up, I'll put that in the first position of the document. Then I'll roll it again and put that word in the second position and so forth. Okay. And so then, because I'm assuming this IID thing, that it doesn't really matter which one was position 43 and which one was position 12, then really the sufficient statistics for estimating the probability of each side of that die are just the overall counts, right? It's the same as when we try to get the sufficient statistics for a coin. Is it going to come out? Which of 2 sides is it going to come out? We flip it k times, n times, and we count how many of those turn up heads and how many turn out tails. Remember the whole thing about maximum likelihood derivation that we did. This is the same thing, only now, instead of having a coin that comes up one of 2 sides, we have a 50,000-sided die. And we're flipping it as many times as there are, say, words in the document. Okay? So, in other words, the sufficient statistics for estimating those probabilities that we need are simply the counts of how many times each word out of the 50,000 appears in spam documents and how many times it appears in non-spam documents. It's exactly the story that we've talked about before. In fact, this is a slide we've talked about before, where we talked about the case of estimating the probability that a die would come up one of 6 sides. Well, same story. And we said, well, we'll have a different theta for each possible side of the die. And then what's the probability, if we want a maximum likelihood estimate for those thetas, we want to use our training data and get a maximum likelihood estimate for the probability that any given word will appear. We're just going to write down the data likelihood. The probability of the data, given some theta, is just the probability that we would get die side number 1 times, remember these alpha? This is the count of the number of times a 1 came up. And this is the count of the number of times for k. And because these are all IID rolls of the die, the probability of any given collection of counts that we observe is just the probabilities of those individual events multiplied together. So this is just what we talked about before, except now we have 50,000 sides. And then we talked about getting the maximum likelihood. And you remember the maximum likelihood estimate is just the proportion of times that the maximum likelihood estimate, for example, for the probability of the word pen, given that it is spam, our maximum likelihood estimate of that is just the fraction of all words in all spam documents that happen to be the word pen. That's our maximum likelihood estimate. And if we want a map estimate, then remember we put a prior on that. And we'd like a conjugate prior so that once we run that through Bayes' rule, we get a posterior that's the same form as the conjugate. And we talked about all that, so this is review. But Dirichlet distribution is our conjugate prior for this multinomial distribution on the number of counts. And that all just, we're just reusing the things we talked about before for coin flipping and dice rolling to get these. And so basically what it all boils down to looks very simple, but now we see all the details and justifications underneath it. What we're saying is we're going to represent each document as a multinomial distributed bag of words. That is, for every one of these 50,000 words, we'll take the count, the number of times that it occurs in a particular document, and that will be our representation. That'll be the summary of all those X sub i's that are in there. All we really need, the sufficient statistics, are just the counts. And then we can get the probability of, this is our X, with this being the count for X1 and the count for X2 and the count for X3. This is our X. And so we can get the probability of this X given Y equals 1 and in general Y equals K. Right? Just by multiplying together the values we got from our training data of the probability of each of these words given the values of Y. Okay. All right. So then in the end, it's all very straightforward. We train our naive Bayes classifier using known spam and known non-spam. We want to get these probabilities of, for example, the probability of aardvark. Well, that's just the number of observed aardvarks over the number of observed words if we want the maximum likelihood estimate. And if we want the map estimate, then we end up, because of that Dirichlet prior, adding in some hallucinated additional words and hallucinated additional subset of them, which we claim are hallucinated aardvarks. Right? Okay, so this really is review of the maximum likelihood map discussion that we had 2 lectures ago. So let me just finish this up by asking, what betas should we choose here? So beta, again, are the priors in our Dirichlet that determine, basically, beta minus 1 becomes this. So the betas are the number of hallucinated aardvark words we want to put in.
Well, actually, it's the beta minus 1 that is the number of hallucinated words.
Well, you can, it's a matter of definition. You can define it as the number of hallucinated words is beta minus 1 or beta. I'm going to define it as beta. So we've got the minus 1 still with us. So what do you think would be a good value for beta? Yes?
Perhaps if you had any data on how often those words normally come up, just or anything.
Good, I like that. So the suggestion is we don't need labeled data to estimate that. Why don't we just take the web or some big chunk of text and look over that unlabeled data? It doesn't tell us whether it's spam or not. Just look at the frequency or the probability that a randomly drawn word will be aardvark there. And that would be an excellent prior, I would think, for aardvark. Of course, now we have to turn it into beta counts. So if we look and we see, the probability that a randomly drawn word in the web being aardvark is 0.00001, then we still have to decide what's our beta. It's not 0.0001, right? It's some hallucinated number of counts. So if it's, let's say, 10 to the minus 5th, then we might choose beta equals 2 for aardvark and 2 for all the other words. And so when we add up all the others, we'll have 50,000 times 2 in the denominator at minus 50,000. And we'll have 50,000, or we'll have 2 minus 1 in the numerator. So we get 1 out of 50,000. Okay, so you see the idea. So, and if we were really confident, then we'd multiply those hallucinated counts by some real big number. If we're less confident, we make them smaller. And the proportions of those counts tell us what prior we're going, relative priors we're going with the different words. And the volume of the total number of counts tells us how confident we want to be in those priors. Or put another way, how much additional observed data is going to take for this estimate to get far away from the prior. Okay. So this kind of, in fact, when you train a naive-Bayes classifier for documents, it's generally a good idea to use map estimates instead of maximum likelihood, because even if you have 1,000 documents, there can be words that occur very infrequently, and so you really do want to put a prior in there to get reasonable estimates and to avoid the possibility of an accidental 0 count occurring for any word. As we talked about before, zeros are bad when you multiply that as 1 of 50,000 terms to get your posterior. Okay? Okay, so that's, and here's the algorithm, very straightforward in the end. If we want to train our naive-Bayes classifier in a collection of documents, we just go through each possible value of y, spam and not spam, for example, estimate the priors. And then for each value of each attribute, that is, for example, in our case, the probability of each individual word in our vocabulary, we need to estimate the probability of that conditioned on y equals spam and y not equals spam. And then given a new document to classify, we just apply our usual machinery to do it. And this works. This actually works quite well. In fact, here's the data set that one of my former students collected, actually, Ken Lang. He collected 1,000 articles from each of 20 news groups. And we could, for example, consider the question of training our classifier to tell for an arbitrary new article which of the 20 news groups should it go into. So now y is not a Boolean variable, but it's still discrete valued. It has 20 possible values, 20 news groups. And if you do that, it actually works pretty well. The solid curve there is the one from naive Bayes. And the way to read this is the vertical axis is accuracy. The horizontal axis is number of training examples. When I say examples, I should be clear. Number of training documents. So there are 1,000 articles from each of 20 news groups, so we have 20,000 documents total. And if we use just the subset of these, say just 1,000 of them to train on, then the accuracy we get is around 70%. Which is pretty amazing when you think about it. What's the, if you guess at random, what's the accuracy you get? 20 possible news groups. If you guess, you get one out of 20 right. 5%. Okay, so here's chance. Chance level is 5%. Starts higher than chance. That's pretty frightening. That's because this log scale does not end at 0. This, I actually remember, this is a 1. So that's with one document from each of the 20 news groups. You already get far above chance level accuracy. Documents vary in length. There is just a random sample. So you can look at these, you can track them down. I believe this is the data, this may end up being the data that's on the homework. Is that true? Okay. But in any case, you can get the data here if you're interested. Yes.
I'm just curious if are there error bars there that are small or are they not shown? I'm just curious if it does really well, but the confidence interval in the one document is huge.
There are no error bars on this, but the test sets are fairly substantial, so the accuracy estimates are within 1% or so. All right, so enough for naive Bayes with discrete valued variables. You guys are experts. You're already in the 99th percent of humanity in terms of expertise in discrete valued naive Bayes, which is good. You should be proud of that. And it also means it's time to move on. So to move on, the question I want to ask is, but what if these values are continuous? What if they're real valued variables? That actually happens a lot, right? So for example, I have some data from an fMRI scanner where we have images of people's neural activity reflected by fMRI. And each image is a three-dimensional picture of neural activity at each of 20,000 locations in the brain. And the value on the ith pixel is some continuous value that ranges, we normalize it from 0 to 128, but it's a continuous real value. And so the question is, what can we do if we have real valued variables? And there are plenty of others, plenty of other continuous values. So a standard way of dealing with continuous valued variables is to not give up on naive Bayes, but instead just say, well, naive Bayes, in fact, is kind of neutral. It makes this this conditional independence assumption, but it doesn't require that we have discrete valued variables. It just requires that we use the training data to estimate this probability and this probability term. And so we just need to make some assumption about how we're going to model p of xi given y in the case that xi is a continuous value. And then, in fact, the most common approach, a common approach, is to use a Gaussian distribution, which, as you'll recall, is just some distribution that says as xi varies in value, there's some kind of probability that xi will take on a particular value that looks like this kind of bell-shaped curve. And if we want to use naive Bayes, all we really have to do is plot, oh, that's too messy. All we really have to do is plot a Gaussian for xi given that y equals 1, and a different one, maybe a different Gaussian for the probability of xi given that y equals 0. And if we do that, then we'll fulfill what naive Bayes needs. And if y is some, let's continue to assume that y itself is discrete. So for example, for the fMRI data, I might be interested in whether or not you're thinking about machine learning, yes or no. And now I have the fMRI image of these continuous valued x sub i's, and I have a discrete valued classification problem. Is this brain thinking about machine learning? So that, in this case, that's all we need are these two kind of distributions. Right? Okay, so let's dig into that a little bit. Just to remind you about Gaussian distributions, here's the formula again for a single variable Gaussian distribution. X is our variable. And so this would be the x-axis, and this would be p of x. And of course, since it's continuous, strictly speaking, these are not probabilities, they're probability densities, right? In the sense that there are an infinite number of possible values of x. And so instead of having all of their probabilities sum to 1, what we want is for the integral over all possible values of x to be 1. The area under that curve should be 1. And because it's a probability density, that means that the probability that x will fall into any particular interval is just the amount of area under the probability density function that's in that interval. Okay, so that's our standard Gaussian distribution. We're going to have, well, let me take one moment just to take this apart. So you see there's a x minus mu over sigma here. That's actually where most of the action is coming from in this function. Mu is the mean of the Gaussian. And sure enough, that term is maximized when x equals mu. Here's mu. And when x equals mu, the probability is maximum. And the further x goes from mu, then the bigger this exponent term is, which has a minus sign in front of it. And so then the smaller the probability gets. And the rate at which that decay happens is determined by sigma, the standard deviation in the curve. And so we have sigma. Okay. And so the expected value or mean value of a Gaussian is given by this parameter mu. And the variance is given by sigma squared. And of course, everybody remembers what expected value means, right? The expected value of some random variable, which is going to be very useful to you on the next homework assignment, is just the sum over the values that it can take on. times the probability that it takes on that value
That's for discrete.
for discrete. And so if it's continuous, we have to do what? We just turn the sum into an integral, obviously. We integrate over all the possible values of x. Right. So the integral is just the continuous version of the sum. The expected value, though. Okay, so that's easy. And what's the variance again? I think of the variance whenever I forget the formula. It's the squared error that I'm going to get if I predict the random variable is going to have a value which is mu. If I'm trying to predict somebody's flipping a continuous value at random something, and I'm trying to predict what value they're going to draw from this distribution, the variance is just the squared error that I'm going to get if I just keep predicting the mean. So the variance is the expected value of the square of the value that actually shows up minus the mean squared. It's just the squared error that I'll suffer if I just keep predicting that it's going to be the mean again. Okay, so that's the variance. All right, so that's the Gaussian distribution. It's easy to use this to model the conditional distribution of xi on y. In fact, as a pragmatic matter, what we need to do is for every possible value that y can take on in every one of our attributes, we're going to want a different Gaussian with different mu and different sigma. As a practical matter, sometimes people decide to assume some of these parameters are shared across the different distributions. So, for example, you might assume that the sigmas are independent of y. That would be true. That would be a pretty reasonable thing, for example, in my fMRI data, because most of the noise, the variation that I see, comes from noise in the machine that really is not a function of whether you're thinking about machine learning or not. It's just the same noise in the machine in both cases. And so it's reasonable to assume my sigma is independent of whether the noise in the machine is independent of whether you're thinking about machine learning or not. So again, if you think about the details of the problem you're working on, you can make appropriate assumptions here. And then training our Gaussian naive Bayes system is very straightforward. It doesn't look any different from before except for one little detail. Again, we're going to use our training data. Now, in the case of brain image data, what does that mean? I'm going to give you, here's a brain image. Person was thinking about machine learning. Here's a brain image when they're not. Here's another one when they were. There's another one when they were, and so forth. And so I'm going to use that. I'm going to go through each of the possible values of y, yes or no, thinking about machine learning, estimate the priors, and then for each of the attributes, each of these 20,000 locations in the brain, I want to learn what? P of xi given y. I want to learn for each of these locations in the brain, what's the Gaussian distribution of activity, the mean and the variance will characterize that Gaussian, conditioned on the person thinking about machine learning. And I'll have to estimate that twice, once when they are and once when they aren't, using the appropriate data from both, the appropriate training data for those two cases. But that's it. So how many parameters? Suppose I have x1 through xn. How many parameters to train this Gaussian naive Bayes classifier? Yes? 4n. 4n? Okay, one vote is 4n. Any other votes? Okay, I think this is pretty good. Let's see. So if we assume this is Boolean, then how many of these do we need? 1. Right. We just need the probability that they're thinking about machine learning. And then we know the probability they aren't is 1 minus that. And how many of these do we need? Let's see, we need different mu for each of the x sub i's, each feature, and also for each value of y, right? We want a different Gaussian distribution. We want to model the Gaussian distribution conditioned on whether they're thinking about machine learning. So we need 2n of these, right? 1 for y equals 0, one for y equals not 0. And how many of these? 2n. Okay, so 4n plus 1 if we include the prior. Okay, so it's still linear in n. I think we had 2n, roughly 2n for the discrete valued one. Here we have 4 because we need 2 parameters, mu and sigma, to characterize the Gaussian, whereas we only needed 1 parameter to characterize the die roll. Okay. Again, the reason somebody asked me after class last time, why do you keep asking us this thing about how many parameters there are? The answer is if you can answer those questions quickly, you really understand the form of the model that we're talking about. And so it's a very quick way for me and you to test whether you really understand what's going on. It would be really good on a midterm or something to ask those kind of questions. All right. So how do we get maximum likelihood map estimates? It's obvious. Maximum likelihood estimates for estimating the mean of a Gaussian is simply taking the sample mean. Have a sample of observations of my brain activity in this location when I am thinking of machine learning. We'll just take the mean value of that. If I want to know the variance, how do I estimate that? Well, as I said before, the variance is just the expected value for the squared error I would suffer if I kept predicting the mean was the value. And in fact, that's exactly the sample variance. Okay, so we can estimate those easily. And it works. We already talked about this. Let me go ahead and look at the outcome here, and then we'll come back to a few questions. So this actually does work surprisingly well. Naive Bayes classifiers. Sadly, I've never actually run the experiment to tell whether we can tell, are you thinking of machine learning? We may have to fix that. But we have tried it with other kinds of problems, such as, is this brain viewing a picture or reading a sentence? Or is this brain thinking about the word hammer or house? Or is this brain confused or actually answering the question that it has been asked? And for all of these, it's possible to train a classifier that does significantly better than chance using Gaussian naive Bayes as the classifier. And just to show you what some of this data looks like, and by the way, this is one of the data sets we'll make available for the course project if anybody wants to play with it. But for example, here's some data where this was collected when we showed people 60 different words. 2 of the words were house and bottle. And what I'm showing you up on top there is part of the 3-dimensional image for when this brain was thinking about the word bottle. And as the thermometer off on the side shows, red means high activation and blue means low activation. The dark blue stuff is just not part of cortex, so we don't even look there. So it looks like 4 images, but it's actually 4 2-dimensional slices of the single 3-dimensional image. And just to orient you, the top of the image there is the back of the head, and is the front of the head. So that's the orientation we're seeing. And actually what I'm plotting here is the average. So we showed each of these 60 words to people 6 different times. And what I've plotted here are the mu's. These are the mu's, the means, for the Gaussian P of x sub I given y. This is the mu's for P of each of those x sub i's, each of those locations, conditioned on y equals bottle. And I could show you another plot of the sigmas. But basically, these are the mu. This is half of the naive Bayes model for bottle. The other half are all the sigmas, which I haven't shown here. Okay? And so then you can see that, of course, since naive Bayes is getting a value which is like that, it's combining the evidence from each of those locations in the brain. In each of these terms, it's getting a different probability. So now if we take a new brain image, we'll look through each of those locations in the brain, and we'll get the probability that this observed activity in this location would have occurred conditioned on our estimate of the Gaussian for bottle. And we'll get another one for the other 59 words. And then we'll assign to this brain image the label that maximizes P of y given x. So you see, now you're on a roll. You could probably zip off a whole bunch of naive Bayes classifiers now. Here, in fact, are the classification accuracies for doing, in this case, it was a Boolean test. Is the person thinking about a tool word like hammer, screwdriver, pliers, or a building word like house, apartment, or palace? And you can see that for each of the different participants in the study, we trained a different naive Bayes classifier because we didn't think people were all identical. And for some of these people, the accuracy is well into the 90s. All of them are significantly better. The classifier is significantly better than the chance level. Half of the words were tools, half were buildings. So if you guessed, you'd get 0.5, just at chance. And so whenever we train a classifier and we try to tell whether it's really working, we should always compare its accuracy against the chance accuracy, which of course would be 0.5. In fact, on this plot, you see, I didn't draw this line at exactly 0.5. Why not? Because I wanted to ask for the number of test examples that it was tested on. I wanted to know what's the level of accuracy where it's significantly above chance, where there's a p-value of 0.05, meaning that we would expect that 95% of the time, even if there's variation in the estimated accuracy due to the small size of the test set, we'd still expect 95% of the time. If the true accuracy is 0.5, the estimated accuracy would be below that gray bar. Yes?
Is it a balanced data set? Do you have the same number? Is it a balanced data set? Do you have the same number of?
This is a balanced data set, same number of tool words and building words. Okay? Okay, so in fact, yeah, this is fun. Once you get into this, it turns out this is the interesting backstory on this is 10 years ago, nobody did this kind of analysis with brain image data. And now it's become a kind of popular style in the neuroscience community for analyzing fMRI brain image data. Part of the reason is it gives you a way of essentially getting, I think of the classifier as essentially a virtual sensor of the information content in the neural activity. So, for example, one thing you can do, once you realize you can train a classifier to decode various mental states, one of the questions you'd like to know is, where in the brain is the neural activity that allows this classifier to work well? So there are a couple ways you could answer that question. But one very simple way I'll call the Rubik's Cube way. So I mentioned there are 20,000 pixels in the three-dimensional brain image. Imagine Rubik's Cube is this 3 by 3 by 3 cube of blocks. So imagine that we trained a classifier, but we only allowed it to use a little geographical region here in the brain that was 3 voxels by 3 by 3. So that'd make it about a centimeter on each side of the cube. Why don't I train a classifier just using those 27 3 times 3 times 3 voxels in the brain and see whether the classifier can decode accurately whether I'm thinking of tools or buildings. And of course, now what I can do is I can move that Rubik's Cube around everywhere in my brain, and I can just record the cross-validated test set accuracy of my classifier for each of those Rubik's Cubes in the three-dimensional volume of my head. And that way I can see where in the brain can the naive Bayes classifier successfully decode whether I'm thinking of a tool or a building, and where can it not. This plot shows the answer to that question. So these red and green colors here are literally the accuracies, the cross-validated accuracy of the Gaussian naive Bayes classifier using 27 voxels, basically a cubic centimeter of brain tissue, to tell whether the person's thinking about tools or building. And you see there are certain areas in the brain where there's a lot of information content that allows accuracies up close to 80% using just the local neural activity in that location of the brain. And then there are other areas in the brain which aren't colored in, which are below 0.7 accuracy, and so they aren't really as informative. But so this is a kind of nice example. Well, I'm a little biased because I like this example, but it's an interesting example of how machine learning methods can make possible essentially the design of virtual information sensors. And then you can use this sensor to roam around and ask, well, is the information coded here? Is it coded there? Is it coded here? And it kind of opens up a new way to look at this kind of data. So there's the story on Gaussian naive Bayes. There's the story on discrete valued naive Bayes. Here's the kind of stuff that you should understand and be solid on. So we started out talking about Bayes' rule and why we'd like to use it as the basis for training classifiers. We motivated naive Bayes. Why? Because we realized how futile it would be to estimate all the parameters for the joint probabilities in all the rows of the joint table. And then we realized with a simple conditional independence assumption, we could shrink that number of parameters to a size that we could reasonably estimate from training data. And now we've seen how to apply that, how to use maximum likelihood as well as map estimates, how to use that with discrete valued variables like words in a document, or continuous variables like continuous activities in the brain. And you should be able now to, for example, answer questions like the ones that I stuck on the slides, and I encourage you to think about in the shower. And maybe ask at the recitation. Okay, see you next time.